Hi, welcome back to Element 14 Presents. My name is Mark. In front of me, you see Spectrum Analyzer for audio. And it has over 3,500 LEDs. But don't worry, we're not going to solder those by hand. In fact, we're not going to use it at all. Let me explain. Over the years, I built many Spectrum Analyzers, and they all have the same purpose: to animate audio in a way it's entertaining. But they all work the same. When you look at this, you see bar graphs, and each bar graph represents a frequency that is present in an audio sample at a certain point in time, a sample. And the stronger it's present, the higher the graphic bar. So basically, an analyzer analyzes the audio and displays the frequencies that are present. That makes sense, right? But what if we take that analyzed data and we use it to recreate the original audio signal? Okay, imagine a piece of sound and you freeze it in time. And then you take the sample of that moment and you analyze it. And you look at the frequencies that are present and you look how strong are they present. So basically what we do is we take the peak value of each frequency and we save that data. And we do that for the next sample and the next and the next and so on. So basically what we get is a whole table with peak data of frequencies. Now the question is, could we use that table to recreate the original audio sound that the table came from? And that's exactly what we do with vocoding. That's right, we are going to build a vocoder. And the vocoder we are going to build is not analog, although I will show you exactly how it works, and you could recreate it with analog technology. But thanks to our digital world, we can do it faster and cheaper, because we're going to use a Teensy and an audio shield and a graphic environment to create this. You only need a few extra parts to tweak the sound you like. And vocoders can be used for many things. You can use, if you're a musician, you can use them, but you might have to adjust the software a little, because the way I program it right now is to emulate a vocoder voice like we have in Battlestar Galactica, the Cylons. So let's get started. So let me walk you through the schematic. It's not complicated. We have an audio shield stacked together with a Teensy. The audio shield will hold an SD card. If you're not going to use the SD card, you need to disable it in the software or it will not work. The audio shield has a line out, so you can just hook it up to a set of speakers. It has a line in and a mic in, but you need to wire that. And today we're only going to use the line in. We have a few potentiometers and a button, and we're good to go. So let's put this all together, let's solder it up and start programming. So when you're going to assemble the electronics, I recommend you use a prototyping board, because that way you have a more stable connection to all the potentiometers and you don't want any wacky connections to mess up your audio. Of course, we have a Teensy. I'm using a Teensy 4.0, and you see it here stacked with an Audio Shield Revision D. Let me just take them apart for you to see. The Teensy already has headers, so you have to put them on, sockets in this case, and headers on this one. And you stack them together and you're good to go. Then we have some potentiometers. A tactile switch is actually a push button to change the function of the onboard tone generator. You will learn more about that later. And of course we have an audio jack. You can decide not to use it and just wire it up the hard way, but this is easier, so I can just connect a PCA speaker. So let's put all of this together and start building. Okay, so first we're going to put the components. I already made a little holes / slots, because the potentiometers, they have 2 pins that are a bit wider than what fits the breadboard, so that's okay, but I did that off screen. So we're just going to place those in there. And the last one is actually going to be the switch, like so. And then this board will place here, and the audio connector we place on the edge. We're going to solder This one, of course, using some sockets because so I can easily take it out. So let's start soldering. So I placed the potentiometers, and now we're just going to solder the pins to the individual islands or pads. Okay, now let's place our audio jack, and then the Teensy with audio board stack we're going to place somewhere in the middle. Okay, so that are all our components. Although this might look a lot and big, that's because of the headers, and you can choose not to use headers and just tag them on directly, and they're a lot flatter, of course. But since I'm always experimenting and I want to be able to quickly take it out, that's why I do it the way I do it. So now let's wire it up. For that, we need to connect the power and the ground to the potentiometers all the same. Make sure you use the 3 volts. And then the center pins we're going to connect to the I/O pins. And of course we have to hook up the audio. Okay, so let's start with the ground wire. That's going to be easy. So that's our ground. Okay, so, oh wait, I almost forgot. I still need to hook up the audio. Now the audio, it's going to be a bit tricky because those headers, or those headers that are on the little audio shield are not in pitch with the prototyping board. So I'm just going to use wires. And the ground is already connected, so I only need to hook up the 2 pins that are closest to the teeny, and then use those for audio. I'm going to solder them directly onto the board. First one goes in there, second one goes in there, flip it over. Yeah, that's going to be it for now. And like I said, it's a prototyping board, so it's fine. So with the connector hooked up, now it's time for the Teensy. So I'll just add the wiring there. So, like so. Left and right is really not important at this time. But, you know, if you meticulously about that, then of course you can sort out left and right. But for me, it doesn't matter. Okay, so with everything soldered up, we're good to go. So let's move on to software and programming. Okay, so the program consists of 2 files. We have a vocoder.h, I'll cover that in a minute, and we have a Cylon vocoder.eno, which is our main sketch. Now I make it a good habit to always include the versions of the libraries that I use after a successful compilation, and I wrote them down here so you can compare and contrast. Then let's move on to the code structure. We have our includes, our variables, our definitions. We have our setup functions in which I will initialize the audio chip. I'll check for an SD card. I define some filter center frequencies. Then I initialize all the audio components to specific values. We'll cover that in a minute. And then I initialize a button function that we're using. And then in the main function, all we do is we handle the user interface, which means reading the button and handle it. We also read a peak value to see if we have any input signal. If not, we will mute the internal generators. If there is a signal, then we unmute it. And then we read and we handle the user interface for all the potentiometers, and we do that every few milliseconds to have it a bit more steady and not fluctuating. Imagine you have a faulty potentiometer and it's keep changing and changing, then that's a lot of processor time, and it might be noticeable in the audio as well. So we only do that a few times a second. And then we play an MP3 file whenever the player is available. So basically it loops a specific file that we specified, and I can, in the user interface, I can just turn down the volume or to turn it off completely so you don't notice it, but it's always there. And that is done by the play function. So that's in short. Then let's walk through the code. This is very important. We have to include the vocoder.h, which is the second file. Then we define some pins that we're using, the connection to the potentiometers. We have some flags, a button initialization, the setup and initialization of the audio chip, and by default we are using the audio input line in. However, the hardware also has a possibility of using an audio microphone, but for now that's switch off. You can use it if you uncomment it and then comment out the section. We check for the SD card, and then we set the center frequencies of our band filters and oscillators. That's determined here, and then later we initialize them, which is done here. We initialize each and every component, and we'll just walk through it quickly because we're going to do that graphically in a minute. Set the low pass filters with some parameters, and then finally we initialize the start of the button, and then we go to the main loop. And in the main loop we just always watch the button. If the button is flagged, then we need to handle it, and then we are going to change the output signal of the internal generator. We can change the wave type. We also look at our peak signal of the incoming audio, and if there's no audio, then it will mute the internal oscillator, and if there is audio, then it will unmute it. And then every few milliseconds, I think right now that's set to 200 milliseconds, but you can change that in the top by the parameters. Every few milliseconds we read our user interface potentiometers and we change the parameters accordingly, like volume out, pitch, the audio wet signal, and so on. And then we play our MP3 file when the audio player is not already playing. So basically what it does is a looping of an audio file, and in this case the audio file is called sd-cylon.wav, and this is actually the function to play the audio file. Now all of this is basically all user interface and some initialization, but it says nothing about the vocoder, because the vocoder is actually completely defined in this file. And don't worry, you don't have to do this by hand. This is basically all the building blocks of the vocoder. And to create this file, all you need to do is create it in the graphic environment and then copy and paste the code, and you're good to go. And the graphic environment is called the Teensy audio tool, and looks like this. Okay, so the audio tool is basically a canvas with all these building blocks, and you can just drag and drop the building blocks onto your canvas. And theoretically I can simply make a throughput of the audio signal coming into the audio board through the microcontroller and send it out directly. Let me see, this is the output and this is the input. Yeah, and then we can just connect the wires. And we do need to add the chip we're using, because I don't want to use the onboard I2S, I want to use the one from the chip, which is this one, the SGTL 5000. And without editing the signal at all, it's from the input, goes directly to the output. And now when I export this and copy it into the sketch, no matter what the main code does, this is always running like a multi-thread, and then it's just doing what it's supposed to do, and it's feeding through the audio while you can do other things. This, for example, is very useful for an MP3 player that we can add. Yeah, there's so many building blocks. I have to play as the wave. Oh, sorry, not MP3, but a WAV file. Play as the wave. Play a file from an SD card. So play a WAV file from the SD card. For example, I could delete this line and send this one directly to there. So as you can see, you cannot connect two outputs to one, but I could connect two inputs to one, but that's a different story. But now, for example, the left channel is feeding the audio through, and the right channel is playing the MP3 file. You do need to use commands in the code. If you use blocks, no, we're using the play SD WAV card, and here you can see what commands you can use. For example, play and then file name. So in your main loop, you say play this file, and it will start playing, while you can do other things. That's how simple this is. It's a very convenient tool, and there's a great tutorial written by the author of the library. Just Google it, the Teensy audio library, and you'll find everything you need to know. This is really worth looking into. Okay, so this is basically the overview of the vocoder, and it's basically made of 3 parts. The first part is our analyzer, in which we basically rip apart the signal, and then we build it up again using this part, and then we have a little part that's called the MP3 player. Now let me start with the first part. Basically, it's best compared with a spectrum analyzer. Let me zoom in. What we have is our input signal, and first thing I do, I create a mono signal from the input. I measure the peak so I can anticipate if there is a sound present or not, and then I feed each filter with the signal coming from the mixer. And the filters are actually, or let's call them channels. We have 16 channels, and each channel has 2 filters, a rectifier and a final filter. And the output of the biquad filter, the final filter, is an amplitude representing the amount of frequencies of that specific band that are present in the input signal. And so we have 16 different signals with different amplitudes that we can use to amplify the output signal coming from these filters. And this is actually where we built the signal from scratch. We have a wave generator. You can also use a noise generator that will have different effect, but I use a waveform, and the waveform has a set frequency that we can change in the by turning the potentiometer later. But the signal coming from the waveform generator is fed to all of the filters here. Again, each channel has 2 filters, and it has a multiplier. And the multiplier is very important because basically until here we have a filtered signal coming from the waveform. If you have noise, then basically if you have like white noise, then theoretically each signal here would be the same in amplitude, but the output signal is determined by the amount of the signal coming from our analyzer. Basically what we do, we take for example, the signal from channel 1 of the analyzer. We use that output to amplify the signal coming from our function generator, the filter signal. So the stronger this signal is present, the stronger the output signal. And we do that for each and every channel. And then we mix them together again, and we add a little delay, and then send it through the output. This long line is directly connected to the input, and we can change the volume of that one with a potentiometer, and that's basically a mix of the input signal with the output signal. And we add a little delay for effect, and of course we have our MP3 player. It looks like a lot, but it is, and I would expect a very big latency because of the many filters and components, but honestly the latency is neglectable. It's actually amazing. When you speak into the microphone, it basically comes out directly and the latency is not noticeable. So this is a very strong tool. We have many options that we can include, but for the vocoder we only need this. And when you're done building, you do the export. Well, we did the import, but theoretically you could do the export here. Export, and then copy and paste this code into Arduino, and then you're good to go. Now let's go back to our sketch. This is our code that we have, and so it's running in the background. Before you compile, if you haven't already, you do need to install the Teensy boards. For that you go to Preferences and Additional Board Manager URL. You have to include this line. Once you put it there, then you press OK. You go to the Board Manager and you install the Teensy boards. Type Teensy, and then you find the Teensy board by Paul Stoffregen, and you install it. And then automatically the audio library is also installed. And then you press a compile and upload. And that's all there is to it. Okay, I hook up the speaker set to the line out, and as line in I'm using a wireless mic. Because it's convenient, I can just talk into the microphone. And while I do so, I can operate the vocoder.
Hi, this is Marv from Alan Fucking. Welcome. By your command. This is the implemented by your command.
And I couldn't resist, I implemented the Cylon sound.
Hi, this is Marv from Alan Fucking. Welcome. By your command. This is the implemented by your command.
I really hope you enjoyed the build today. I'm sure I did. And remember, there's a project page at the Element 14 community. You can visit it and download all the information you need to recreate this awesome project. If you have any questions or suggestions, you can leave comments and I'll do my best to answer each and every one of them. So this is all I have for you today, and I'll see you next time.